In this lecture, we'll discuss how to draw state table for all four types of state machines or pattern detectors or sequence detectors. If we want to draw state table, first we need state diagram or state graph. So first we'll see for mealy overlap. So I drawn the state diagram for the pattern 1001. Now we'll see how to do state table for this diagram. So this is mealy overlap. Mealy overlap. So the format of state table is present state PS, next state NS. In the next state, we have to write input value for 0 and input value for 1 also. Okay. See here in the diagram, numerator can be 1 or numerator can be 0. That input can be 1 or 0. Here I assumed my input as X. You can assume anything. And we have to write output also. We have to write output value when X equal to 0 and when X equal to 1 also. Here I assumed my output as Y. See here, when X equal to 1, what is output? This denominator is output. Or when X equal to 0, what is output? Okay. So for example, for this, if you see, when X equal to 1, when X equal to 1, what is the output? When X equal to 1, what is the output? That we write here, according to the state transition. Okay. So in mealy, we know if there are 4 bits, then we'll get 4 states. I listed states here, S1, S2, S3, S4. So these states we have to encode. Suppose in your memory, if there are 4 locations, how many addresses you need? 4 addresses. So for 4 states, if I want to encode in binary, I need 4 combinations. 0, 0 with 2 bits. We can create 4 combinations with 2 bits, no? So to create 4 combinations, 2 bits enough. So 0, 0, 1 combination, 0, 1, 1, 0, 1, 1. This order no matter. We can write any order, this 0, 0, 0, 1, 1, 0, 1, 1. Okay, right. So now see how to draw this state table from this state diagram. So initially I am in a reset, nothing but S1. So my present state S1, wherever I am, that is my present state. So when I get input 1, where I am going? S2. So when I am in present state S1, when I got input 1, I went to S2. But when I am in S1, when I get input 0, I am at S1 only. So when I am S1, when input is 0, I am at S1 only. So like that we can write all these things. Now we'll see for this, we see output also for this. So when I am at S1, when input is equal to 1, my output is 0. Okay. When my input is 1, this one is this one. What is my output? 0. 0. That 0 I have to write here, this 0. This same input x1 is the same input x1. This is the output value. Okay. Suppose when input is 0, this input is 0, nothing but this 0. What is my output denominator? 0. So my output I will write here, 0. Okay. Like that we'll see for last combination. Second and third you can do according to the first combination. Suppose now S4. When I am at S4. When I am at S4. So this will become present state. So my present state is S4. When input equal to 1, where I am going? S2. When I am S4, my input equal to 1, I am going to S2. That time what is the output? See, 1. That time what is the output? 1. But when input is 0, I am going to S1. See, here when input is 0, I am going to S1. At that time what is the output? Denominator 0. That 0 we have to write because this is x0. Okay. Like that we have to do. Suppose this is present state when I am here, this will become the next state. But when I came here, this will become the present state. Okay, that we have to observe. Now we'll see state table for mealy non-overlap. This is the diagram, state diagram. So from this we'll try to draw state table. So present state, next state, input 0, input 1, and output when input 0, output when input 1. This is same as previous we did. Okay. There is nothing new here. Only diagram will change according to this table will change compared to previous. Okay. So you can do this also according to previous. Now we'll see state table for more non-overlap. Okay, compared to mealy, the state table will little differ at this output place. Okay, there in mealy we write output for x equal to input 0 and input 1, but here we don't write like that. Remaining everything same. And one more thing is here we will get one extra state because this is more na. Okay, because of one extra state, total here 5 state for the same pattern. So if there are 5 locations in the memory, we need 2 bits are not enough, no? So we need 3 bits. So that's why we are encoding with a 000, 001, 010, 011, 100. That we have to observe. Okay, out of 8 combinations, we can allot any combinations to these 5. Okay, now here, see, now I am at S1, present state, this S1. When input is 1, I am going to S2. When input is 1, S2. But when input is 0, I am at S1 only. Okay, but here pattern not detected, that's why 0. We'll see this combination. Suppose when present state is S4, when I am at here, when input is 1, I am going to S5. When I am at here S4, when input is 1, this is 1, I am going to S5. That time pattern is detecting, no? So I have to write here 1. Okay. So in Moore, at output only one place we can get 1. If this is 1, all others we can blindly write 0. Okay. So when we are at S5, when input is 1, we are going to S2. When at S5, when input is 1, we are going to S2. But when 0, we are going to S1. Okay, right. Finally, we will see the state table for Moore overlap. So this is the state diagram. From this, we'll try to do state table. See, in Moore, we get bits plus 1 states. So 4 bits. So we'll get 5 states. So this is also according to previous we can do, because here a diagram will change, so the table will change. Remaining process everything same. So you can do accordingly. So one point we can observe. So here we are getting 3 bits in Moore for same pattern for one state, but in mealy for same pattern for one state we are getting 2 bits. 3 bits means 3 flip flops. 2 bits means 2 flip flops. So Moore is more complex compared to mealy. Okay, right.